initialize Genesis sequence.
Wow, fantastic to see so many people interested in learning more about garbage collection. My name is Stefan Johansson. I work in the Java team at Oracle doing garbage collection. And I want to welcome you guys to this presentation, Garbage Collection in Java, the progress since JDK 8. I have two goals with this presentation. First, I want you guys to learn more about GC in general, hopefully helping you out when choosing which garbage collection algorithm to use. But I also want to show all the great progress that we've made since JDK 8 and hopefully encourage you guys to try out a more recent version of the JDK if you're still on JDK 8. So with that, let's take a look at the agenda. So the presentation is divided basically into two parts to cover those two goals. So first, we'll look at GC in Java and closer at the different collectors. Then we'll look at some performance numbers and a few success stories from the real world. And hopefully we have time for some words about the future in the end and some questions. But let's get into it. So garbage collection is a key feature of the Java platform, allowing you as users to focus on solving your problems rather than thinking about low-level memory management problems. So Java is a type of automatic memory management, and we want to solve two things: fast allocations and very efficient reclamation. The fast allocation part is handled more or less the same regardless of which GC algorithm you're using. So we have something called TLABs, thread local allocation buffers, that are handed out by the GC to the allocating Java threads. Then you can do very fast pointer bumping allocations without any synchronization in the Java threads. Once the TLABs are full, they are handed back to the GC, and you get a new TLAB in the Java thread. And there are, of course, some synchronization going on there. But overall, it's very efficient and handled more or less the same regardless of the GC. What differs is how we handle the efficient reclamation. And we're going to look closer at that. But first, I want to talk about the reason for having multiple GCs. We sometimes hear, why do I have multiple? Why not just have one that does everything? And the main reason is that the Java platform is so large, it supports so many different use cases, that it's extremely hard to have a single GC that can solve all the problems. We need to be able to handle batch processing, UI applications, small or large cloud services, or basically anything should be able to be handled by the Java platform. And it's extremely hard to create a GC that's optimal for all those use cases. But let's look closer at how we do the memory reclamation part. So first, we need to determine the liveness. And what we mean by that is we need to figure out which object do we need to keep alive for the Java application to follow the function correctly. And we do that by tracing the object graph. And what that means is that we start off with a well-known set of roots, and that is objects that we know need to be kept alive. So for example, objects on thread stacks, static fields and classes, and a few other things that we need. Unless we keep those alive, the Java application won't work. When we have those objects, we follow references in those to other objects. And that way, if we continue doing this, we figure out all the objects we need to keep alive in the Java heap or the part of the Java heap that we're currently collecting. When we have this liveness information, we're able to reclaim the memory. And there are a set of different techniques to reclaim memory. You can either keep free lists, knowing this is where we have free memory, you can allocate in here, or we can do something that's called compaction or copying, where we copy the objects that we need to keep alive to a new location, making sure that we store them in a compact manner without any space between them, and then we can free up the original location, freeing up the unused memory. And yeah, there are a set of different techniques for most of the problems that we occur, but those are two of them. Then we need to figure out when to do the garbage collection work. Either we do it while we have the Java thread stopped. We call that a stop the world collector. And that's doing work in a GC pause mainly. Or if we want to do the garbage collection work while the application threads are running, and we call that a concurrent collector when we do garbage collection work at the same time as the Java application is running. And of course, we want to make this as efficient as possible. And there are many techniques for making it more efficient. One of the most important one is called generational collections. And what we mean by that is that we divide the heap into two generations. A young generation where we store newly allocated objects, and an old generation where objects that are long-lived are promoted to. So objects that have been around for a few GC cycles are moved to the old generation because they seem to stick around. And the reasoning behind this is something called the generational hypothesis, which basically says that objects are only used for a short period of time. Newly allocated objects are only used for a short period of time. So making use of this, the idea is that we collect the young generation at a cheaper cost. So very few objects in the young generation is supposed to be kept alive. And if it holds, we make a much more efficient garbage collector because it's much cheaper to collect the young generation compared to collecting the whole heap. So now you know a bit more about how garbage collection knows, but what might be more important to you guys is which GC to choose are the ones that we have available in OpenJDK or Java. And to know that, you need to figure out what's the main focus of your application. And we usually talk about three different aspects here when we design GCs and try to focus them on different things. The first being throughput, and what we mean by that is basically the raw number of transactions that you can complete in a set amount of time. Then we have latency, and that's more focused on the time it takes to complete a single transaction. So for example, if you have a long GC pause, that will inflict latency on your transaction, and that will affect the latency of your application. The third one being footprint, and that's more or less the overhead caused by the garbage collection algorithm in terms of additional memory used or additional CPU resources used. And again, from a GC developer's point of view, it's extremely hard to optimize for all of those at once. So usually we have to do a few trade-offs trying to decide what should this garbage collector focus mostly on. And if we try to illustrate this a bit, we can have something that looks a bit like this. We have a set of application threads that run. At some point, we realize that we need to do garbage collection work to free up memory. We do that as efficiently as possible using multiple threads, but still we have a GC pause before the application threads can run again. From a throughput perspective, this is very good because the application threads can run without any interference of the GC threads, but we have the GC pauses which will inflict latencies. So if we want something that is more latency aware or good from a latency point of view, we could have something that would be illustrated like this. So we have much shorter GC pauses, but then instead we do garbage collection work while the application threads are also running. So from a latency point of view, this is way better, but as you can see, the application threads might have to compete for CPU resources with the application, and there is a competition between the application threads and the GC threads. So a bit worse from a throughput perspective. In OpenJDK today, we have 5 different garbage collectors. We have Serial, which has its main focus on having low memory footprint. We have Parallel, which is a throughput-oriented collector. We have G1 with a balanced performance profile, trying to achieve both good throughput and low latencies. Then we have the 2 newest additions, CGC and Shenandoah, which are focused on low latency. At Oracle, we maintain 4 of those collectors, Serial, Parallel, G1, and CGC, and those are the ones that I will be focusing on today. So let's look a bit closer at these different collectors. We first have Serial, and as I mentioned, the main focus of Serial is to have very low memory overhead and not add additional native memory usage when using the Serial collector. It supports generational collections, and the heap layout can be illustrated like this, a bit simplified, but you have a young generation and an old generation. The sizes of those are decided upon startup, so it's not a very flexible heap layout, but that's how it was done in the beginning of time. And Serial does its garbage collection work, stopping the Java thread and just using a single thread to do the garbage collection work. So if you have a large heap, this might not be an optimal solution, but then for services or things running in small containers, this might be a pretty good alternative, since you might just have a single CPU to do the garbage collection work anyways. If we move over to Parallel, it's, as I mentioned, throughput-oriented. Again, similar heap layout compared to serial. It supports generational collections. And the big difference compared to serial is that it uses multiple threads to do the garbage collection work. And you can see that this is the same illustration as we had on the previous slide. So it's really how a throughput-oriented collector works. Parallel was the default garbage collector up until JDK 8. So if you have any applications running on JDK 8 and you don't specify your GC, you will most likely be using Parallel GC. Let's move over to G1. It strives to have a very good balance between latency and throughput. And one of the key things that G1 want to avoid is the worst case latencies that you sometimes can see with Parallel. So as you might remember from the previous slide, Parallel did all its garbage collection work in the GC pauses. That means if the old generation eventually fill up, which it most of the time does, you will have to collect the old generation in a single GC pause. This is something we try to avoid with G1, and the way we do this is that we have region-based heap layout in G1. So as you can see, this differs a bit compared to serial and parallel, that we divide the heap into evenly sized regions. Those regions can then belong to either the young or the old generation, or of course be free if they're not currently used. And it's not like a region is tied to a generation for the span of the application lifetime, but this differs over time. So a much more flexible heap layout. Then G1 also supports concurrent marking. And what we mean by that is that alongside the application threads running, G1 can determine the liveness of the old generation regions. So we're able to figure out which objects need to be kept alive in the old generation without stopping the Java threads. Those two things together, the region-based heap layout and the concurrent marking, allows G1 to do something called mixed collections. And mixed collections are collections where we collect the young generation together with a few old generation regions in a single GC pause. And doing multiple mixed collections, we're able to collect the whole old generation without having to do it in a single long pause. So that's how we avoid the worst case latencies with G1 that you sometimes see with Parallel. Something that we also worked hard on with G1 is to make it easier to tune. So we have this main tuning knob, which is the pause time goal. In G1, the default value of this pause time goal is 200 milliseconds, which means that by default, G1 will try to keep the pauses below 200 milliseconds. And for some services, this might be way too much. And then it's easy to tune this down to, say, 50 or maybe 100 milliseconds to see if that works well, getting better latencies. And for some workloads, it might be better to tune it up if you want better throughput performance. We made G1 the default garbage collector in JDK 9. So anything running on JDK 9 or a newer JDK is most likely using G1 unless you specify something else. Then we have the newest addition, CGC. Its main focus is low latency, but we also want CGC to be very scalable. And what we mean by that is basically we want sub-millisecond pauses, and we want to be able to handle terabyte heaps. And the way to achieve this is to make sure that the GC pauses don't scale with the heap size. Similar to G1, CGC is region-based, but the big difference is that CGC does the collection work fully concurrent. So all the heavy GC work is done concurrently with Java application threads running. We still have the GC pauses here, as you see, and you recognize the illustration, but they are very short and they are mainly synchronization points so that the GC and the application threads can decide on what phase we're currently in. Are we doing marking, determining liveness, or are we moving objects around and updating pointers to where objects are located? And we need GC pauses to synchronize this. For this to work efficiently, CGC makes use of something called load barriers. And this is highly optimized code that the Java application threads will run without you knowing it when they access an object to figure out if it's safe to use this object right now, or if we need to update the location where this object is located, or actually if we need to help out move an object. Because when you have a fully concurrent collector, it might be that your application threads help out doing some GC work if they are the first one encountering an object that's supposed to be moved. So that's pretty cool. We added support for generational collections to CGC in JDK 21. In JDK 21, you need to enable the generational mode with a separate flag, which is called cGenerational. But in JDK 23, the generational mode of CGC is on by default. It's not the default GC, G1 is still the default, but when using a CGC, you get the generational mode. And yeah, it's working very well. So let's do a quick summary on the garbage collection that we have. We have serial, which has low overhead, and it's very suitable for small containers. We have parallel with great throughput, suitable for workloads where the worst-case latencies are acceptable. Then we have G1, good throughput, controllable latency, and suitable for long-lived services where the heap sizes are below 16 gigabytes. The 16 gigabytes here is just a guideline. G1 can handle much, much larger heaps. It's just when you go above 16 or 32 gigabytes, CGC might be a better alternative. And then CGC, good throughput, ultra-low latency, suitable for long-lived services where the heap sizes are above 4 gigabytes. And same thing goes here. CGC can be used with smaller heap sizes. It's just that it shines the most the larger the heap gets. And I usually say that you should always evaluate at least 2 of the GCs for your application to see how they behave using different algorithms. So keep that in mind. And yeah, that's the finish of part 1, the general information about GC in Java. So now let's look closer at the performance improvements that we've seen since JDK 8. So JDK 8 was released over 10 years ago, but it's still heavily used in the Java world. There have been significant improvements when it comes to performance across all areas in the Java platform. And this is true if you look at areas as GC, Git compilation, the JDK libraries. Everything has improved over those 10 last years. And it's also true if you look at the areas within GC. So the GCs have shorter pauses, we have lower native memory overhead, and we have better overall throughput. And you might remember that I said it's very hard to optimize for all of those. And the way we've done that over the past 10 years is that we've cut away some of the old trade-offs that we made in the past and came up with better solutions to solve those problems that are more efficient. So a lot of work has gone in here, and of course, we also added new low latency collectors to make the Java platform even more suitable for most workloads. I'm going to show numbers using a benchmark called SpecJBB 2015. It's a pretty well-known benchmark. It's developed by the Spec organization, focusing on benchmarking. It provides 2 scores, which is very interesting from a GC point of view, or at least the 2 scores are interesting from a GC point of view. The first one is raw throughput, so that will show the progress of the whole Java platform, including GC, but also the other parts. The second score is throughput with latency constraints, and this score is heavily affected by the GC pause times. So when we improve those, we will see improvements in this score. So that's why this benchmark is pretty good from a GC point of view. I'm comparing the collectors individually, so I'm not trying to show you which collector is the best one, because depending on which heap size I would choose, the answer would be differently. So instead, I want to show the progress for each GC, because for some of you, parallel will be the best choice, for some of you, G1 will be the best choice, and for some of you, CGC will be the best choice. I'm not including serial in this comparison, because this benchmark doesn't make sense with serial. But let's start with looking at the throughput numbers. So I'm using JDK 8 as the baseline for parallel. And as you can see, moving to JDK 17, we get a 30% boost in performance by upgrading. And part of this is due to improvements in GC. Parts of this is due to improvements in other parts of the Java platform. Going from 17 to 21, we don't see as much improvement, but still a small boost. We should keep in mind here that between JDK 8 and JDK 17, it's something like 7 years of development going in, while between 17 and 21, it's only 2 years. So more time to do improvements between 8 and 17. If we look at G1, the improvements are even bigger, more than 40% improvement in throughput, which is great. One reason for this is that G1 was a bit worse in JDK 8, so there was more room for improvement, but also that we spent more resources on G1 since JDK 8 compared to parallel. If we move over to CGC, we see that we're not comparing JDK 8 because CGC wasn't around in JDK 8, but instead we're using JDK 17 as a baseline because that was the first long-term support release where CGC was fully supported. And then we compare it against JDK 21, where the single generational mode was still the default one, and JDK 23, where generational CGC is the default version of CGC. And as you can see, adding generational support to CGC gave us a 10% boost when it comes to throughput performance. So a pretty good improvement there, kind of what we expected and hoped for. So nice to see that progress. Let's move over and look at the latency scores instead. And starting off with parallel again, see more or less the same improvement, maybe a bit more, 40% improvement in the latency score. So really nice to see this again. And in the latency score, shortening the pauses is really what affects the score, because if you have long pauses, that will affect the application latencies in the benchmark, giving a worse result. And one thing that we did to improve the latency, so the GC pauses in parallel GC between 8 and 17, was that we streamlined the underlying threading system of parallel GC to use the same one as the other GCs. And that turned out to be a big win because the threading system for the other GCs was way more efficient compared to the one used in parallel back in the day. So by streamlining our code, reusing stuff, we were able to gain some really nice performance, which is great to see. If we move over and look at G1 from this perspective, the improvements are even more impressive. We doubled the score between 8 and 17, an additional 10% between 17 and 21. And it's really nice to see that all the hard work that we put into G1 really paid off, because for G1, we worked so hard on making sure that every part of the pause was made as efficient as possible between those releases. So really nice to see that all the hard work really paid off. When it comes to CGC, the improvements aren't as visible. We get some 5% improvement going to generational CGC. And you might be surprised by this because CGC is a low latency garbage collector focusing on this. Why don't we see a bigger improvement? Well, the reason behind that is the latency score in JDK 17 was already so good with CGC, so improving it is extremely hard because the GC pauses in CGC is very short and they don't really affect the application latencies anymore. To look a bit closer at this, let's look at the P99 pause times with SpecJBB. I'm using a slightly different mode of SpecJBB here with a fixed load to make it more sensible to look at the pause times. And again, it's normalized to try to show the progress rather than the raw numbers. And as you can see, we cut away 40% of the pause time, the worst case pause times between 8 and 17. And then they were kept more or less on the same level between 17 and 21. And the same goes for G1. The big difference again is between 8 and 17. But still some additional progress between 17 and 21. And for CGC, the improvements aren't as big, but still the generational mode cut away 15% of the worst case latencies, which is nice. But still, this doesn't show up in the latency score. And to really make it obvious, but make it a bit more obvious why this is the case, let's look at the raw pause times. And mind that this is a logarithmic scale, and that's why the improvements to parallel in G1 doesn't look very good anymore. But you can see that we cut away much of the pause times, as we saw on the previous slide, down from around 100 milliseconds to somewhere around 65 milliseconds with G1 in parallel, which is great for those collectors. But compared to the pause times of CGC, we're in a different order of magnitude here, because we have 140 microseconds in JDK 17, which is down to 120 microseconds in JDK 23 with generational CGC. And reducing those extra 20 microseconds, they don't really affect the latency score because the application latencies are measured in tens of milliseconds in that benchmark. So that's why this doesn't really show up in the benchmark score. The last thing I want to show you guys when it comes to this benchmark is the peak native memory overhead. And for parallel, it's pretty boring. It's been on a very stable level from JDK 8 to JDK 21. If I would have included JDK 23 for parallel, we would have seen some improvements here as well, because some of the things that we did for G1 into 21 were transferable to parallel as well. And looking at the G1 chart here is much more fun. But again, we spent a lot of more resources on G1. One of the biggest problems we saw with G1 in JDK 8 or heard about was the additional native memory overhead. And the big reason behind this is a data structure called the remember sets. The remember sets are needed to be able to do those region-based collections that I mentioned earlier. So to be able to collect the old generation regions, we need to have remember sets for them. That's how we know what needs to be kept alive and things like that. But the implementation of remember sets in JDK 8 kept them around for the span of the application's lifetime. So they were never freed up, or at least not freed up in an efficient way. But we realized we only need those when we do collections of the old generation. So only when we do mixed collections, we need the remember sets. So let's rebuild them while we do the concurrent work. And this was a feature that was put in between 8 and 17 to rebuild the remember sets during concurrent marking. And by doing so, and also making sure that the remember sets data structure were more efficient in terms of memory usage, we were able to cut the memory usage almost in half. So down from almost 2 gigabytes to somewhere around 1 gigabyte. And this effort in reducing the remember set overhead continued into 21, making sure that we have the most, or at least the more efficient implementation of those data structures. But along with this, we came up with a better trade-off on how to solve some other problems in G1, keeping track of liveness information and things like that. Because up until JDK 21, G1 had 2 marking bitmaps. And a marking bitmap is a data structure handling liveness information for the old generation. And we needed 2 for reasons, and we came up with better alternatives to those reasons, and we're able to remove one of the bitmaps. And for a 16 gigabyte heap, that is 256 megabyte of additional memory that we could reuse. So that's a pretty good saving. Moving over to CGC, we see the memory usage going in the other direction with generational CGC. And again, this is one of the trade-offs that I've been talking about earlier. To be able to do the generational collections, we need to keep track of more information. We need to know about pointers between generations, and we need to have more forwarding information where objects are moved than we needed with single generational CGC. So for me, it's very hard to see this as a regression. I see this as an active choice, because having generational collections is such an important feature for a garbage collector. And going forward with CGC, we're planning to remove the single generational mode, and that's also a pointer towards this being the correct choice. So if you want to dig deeper into those numbers, I have a blog post that I put out when JDK 21 was released. More or less the same numbers. I refreshed them a bit for this presentation, but more or less the same information there. I have some more performance numbers that I've generated using Cassandra. As most of you know, it's a distributed NoSQL database. It's widely used, and it's a proven technology. It's used by us in the GC team because it's a good way for us to run something that is pretty real-world-like. Just using the normal benchmarks, it's good, but it's better to run something that we know is used in the real world. And it's very much highlighting many of the aspects that we're interested in when it comes to memory usage, pause times, and throughput. So I have 2 slides here that I want to share with you guys. And here I'm comparing Cassandra using JDK 21, and I'm just focusing on CGC and G1. And the red line is single generational CGC. The green line, as you understand, is generational CGC. Then we have 2 lines for G1, the first being G1 with the default pause target, and the one at 50 milliseconds is with a 50 millisecond pause target. The first slide here, we're looking at the average latency. And as you can see, the G1 lines are the ones that are working best, even though generational CGC is very close by. And looking at the average latency is more of a throughput metric, so that's why G1 look a little better compared to CGC here. Generally, G1 has slightly better throughput compared to CGC. And what we're looking at here on the x-axis is the number of clients. So I'm adding more and more clients, stressing the system more and more, and seeing how that affects the latencies. And on the next slide here, we instead look at the 4/9 latencies. So the worst case latencies in a system where we're increasing the load. And what we're seeing here is that single generational CGC falls over when we add more clients than 75. And what's really happening here is that CGC start experiencing something called allocation stalls. And allocation stalls is what happened when CGC, since CGC is a concurrent collector, it's freeing up memory while the application is still running and allocating more objects. So if you run into allocation stalls, that means that CGC haven't had time to free up memory fast enough to satisfy allocations coming into the system. So the threads are stalled. And when you see this with CGC, you should really look at your configuration, either adding more heap size to CGC or increasing the number of concurrent threads, because CGC can't keep up. Or you switch over to generational CGC if you're still on single generational CGC, because as you can see, generational CGC is handling this way better, and best of all, with a pretty wide margin. I should also mention, it says here it's using a 32 gigabyte heap. The ones of you that really cares about details should know that G1 is actually using a slightly smaller heap than 32 gigabytes to be able to make use of a feature called compressed OOPS. And sometimes compressed OOPS is talked about as a very important feature that CGC can't support. But we see here that even though CGC can't use compressed OOPS, but G1 can, CGC is still performing better. It's really nice to see that the default pause target, G1 is able to keep below that for the worst case latencies. We see that for the 50 millisecond pause target, the worst case latency creep up over this, so we probably have some work left to do here, trying to keep those below the 50 millisecond pause target. But still pretty nice to see that it's so easy to change the latency profile of G1 by just using a single flag to push down the latencies even more. Yes, so now let's move over to the success stories from the real world. The first company that I want to talk about is Netflix. As many of you might know, they have a really large stack of Java application. And they started looking at upgrading to JDK 17 somewhere around 2022. And they worked very hard on their internal data structure or infrastructure to make those upgrades easy for the different application owners. And they saw really significant performance improvements by going to JDK 17 from JDK 8. Most of their application on JDK 17 are using G1, and during this time, when they did those upgrades, they published this chart. And what we're looking at here, the blue line is the time spent doing GC. The gray area is the same metric from last week, so to make it easy to compare. And then we have the brown line, which is the average pause time. And that one is connected to the right y-axis. So as we can see, the pause times are down to almost half, and the time spent during GC is down, I think, almost half as well, or maybe even a bit more. So pretty nice to see the same improvements that we see our internal benchmark actually show up in the real world as well. But Netflix wasn't really happy with just this. They started looking at upgrading to JDK 21 I think this year or late last year. And one of the big drivers behind this was interest in evaluating generational CDC. And they've written a really great blog post about using generational CDC. And you can find this using this QR code. They had expectations going into this using generational CDC that it would be mostly useful for really, really large heaps. Again, caused by this expectation that since CDC can't use compressed oops, it wouldn't really work well with heap sizes below 32 gig. But they were surprised, and they actually use generational CDC by default for any application running on JDK 21 or later. So as an application owner at Netflix, you need to opt out of using generational CDC if you're on 21 or later. And I picked up a quote from this blog post that I think is very important. Left unquestioned, assumption and expectations could have caused us to miss one of the most impactful changes we've made to our operational defaults in a decade. We'd encourage you to try generational CDC for yourself. It might surprise you as much as it surprised us. And the surprise here, again, is how well generational CDC worked on smaller heap sizes. At Netflix, getting rid of the tail latencies is really, really important because they lead to a lot of errors. And even though you might not get as high throughput on smaller heap sizes as some other collectors might give you, you get rid of those tail latencies and you get rid of problems. So really nice to see this from the real world. We as GC developers are very happy about that. The next company I want to share information from is Mercado Libre. They are the largest e-commerce, fintech, and logistics company in Latin America. They are present in 18 countries with more than 100 million active users, and they also have a lot of Java microservices, more than 8,000 of them, and they are also looking to upgrade to Java 21. They currently are mostly on JDK 17, but again, the driver behind this upgrade, or the wanting to upgrade, is both Loom and generational CDC. I couldn't get any charts from Mercado Libre, but I got this extremely long quote instead, so stay with me. Mercado Libre is starting the journey of migrating over 8,000 microservices to Java 21. As an early step in this transformation, we migrated our streaming data service, which handles over 10 million incoming requests per minute and 40 million outgoing requests per minute, to Java 21, leveraging Loom and generational CDC. This migration resulted in significant performance improvements, including a 50% reduction in threads, a 25% reduction in CPU usage, a 20% reduction in memory usage, a 30% reduction in latency, and a 25% improvement in garbage collection indicators. These gains not only improved our response times, but also enabled us to handle the same traffic volume with fewer virtual instances, optimizing our infrastructure costs. This demonstrates the power of Java 21, Loom, and generational CDC in enabling high-performance, scalable data streaming applications. And yeah, thanks. I mean, from our point of view, this is great. We should mention, or I should mention, that this is just not a straight upgrade. They actually did some changes to the code to really leverage Loom. I suppose we're talking about making sure that they use the correct type of locks instead of synchronized and things like that. But this wasn't a big effort for them. And getting those gains by just using the latest Java release is pretty amazing. And yeah, if you're on an older release, hopefully this help you in deciding to upgrade. The last external, or actually internal, this is from an Oracle team in the Oracle Cloud Infrastructure. They are also looking at upgrading. A lot of the services in the Oracle Cloud has been on older JDK releases, and since you get free performance, they are looking to upgrade. The object storage team is no different. They are mainly a throughput workload, but they also care about the time to first byte. So what GC do we have that is balanced between latency and throughput? Well, G1. And it turns out that they were using G1 in JDK 8. And doing an upgrade to JDK 17 showed some really good improvements for them. So we here have a chart showing their get and put. So they are an object storage, just storing and getting data from the cloud. We can see here that during the upgrade, they saw a pretty significant boost in performance indicators for both get and put, which is really nice. And again, if we look at the time spent in GC, this is looking at collecting the young generation. We can see that the amount of time spent in that went down from around 1% down to something like 0.5% of the application runtime. So pretty great to see. A short quote from them as well. We have strong data showing that the JDK 17 upgrade has improved our throughput with roughly 20% using G1. So very nice to see. So we actually have a lot of time for the future. Guess I'm quick. So going forward, we really aim to keep improving. We have a lot of exciting features lined up for CGC. The way CGC is implemented, the implementation details allow us to do some really cool idea, or we have a few really cool ideas of what we can do going forward, improving how GC is done. So that's very exciting. When it comes to G1, something that we've talked about for a very long time is to improve the throughput performance. As you've seen in the slides, we've improved the throughput quite a bit already. But you might remember I mentioned that CGC makes use of something called load barriers. In G1 and all the other collectors that support generational collections, we also have something called write barriers. So every time you write an object, some additional code is run by the JVM. And with G1, those barriers are much more expensive compared to parallel. So that's usually why we see a bit worse performance with G1 compared to parallel. Going forward, we have a few JEPs lined up. One is going into JDK 24 now to make it easier to experiment with the G1 barrier. And we've already started experiments trying to move the G1 barrier to be more similar to the one used by parallel. And yeah, the performance results look really promising there. So hopefully, going forward, we can see even better throughput scores with G1. The last thing is, of course, to keep improving on footprint. I mentioned that with parallel, we already improved compared to JDK 21. You saw with generational CGC that the memory usage has gone up, and we have ideas on how to reduce this, making sure that we only use the additional native memory that we actually need to be able to support the collections. So we have ideas across all areas on how to keep improving the GCs in Java. So hopefully, you can continue to upgrade and get free performance. So if you want to stay informed, we have this document, the GC tuning guide, that we try to update for each release. It has some basic guidance when it comes to performance tuning. We have the Java developer portal at dev.java, which is a landing point for Java developers with a lot of great articles. Then like news and views from the likes of me at inside.java, where us in the Java team, when we write blog posts and videos like this will become, they are posted on inside.java. So a lot of good content there as well. If you want to join the discussion, be part of developing OpenJDK, you can join the mailing list on openjdk.org to see what's going on in OpenJDK. If you're interested in watching and looking at the JDK code, it's available on GitHub /OpenJDK. And of course, you can follow Java and OpenJDK on the social media platforms. So this is my last slide. The key takeaways, well, there have been massive improvements since JDK 8. So if you're still on that, you need to upgrade, or you should at least really try to do it, because it will help your performance quite a bit. And then it's very important to choose your GC wisely. Depending on what your application is trying to do, choosing the right GC can really have big performance implications. And then lastly, keep upgrading, because once you move past JDK 8, moving to an even more recent release is much less of a hassle. And with that, I'm done, and we have 5 minutes for questions, so shoot. Thank you. Any questions? Yes, there.
What about Java 11?
Yes, so the question is, what about Java 11? Well, I didn't fit it into the slides. If I actually have a blog post, like the link to the blog post, I have an older article which compares 8, 11, and 17 that I put out when Java 17 was released. So I would say that the performance of JDK 11 is somewhere between 8 and 17. So you still have some improvements going to 11, but not all of them. And yes, question here.
Do you have recommendations about managing native memory overhead besides try and error?
So the question is if I have any recommendation for managing the native memory other than trial and error. You can't really manage it yourself. You can monitor it. There is this feature on the Java platform that's called native memory tracking, which you can turn on to get, and together with JFR, you can get continuously information about how much native memory the different parts of the JVM is using. So, for example, both the GC and the JIT compiler uses additional memory, and the class, like loaded classes and things like that. So you can get pretty much information about that using native memory tracking, and it's easy to see the information using JFR. But there's no easy way to really tune that. You can, of course, for when it comes to compilation, you can set like a max size on how much you can use for that and things like that. But really managing it during runtime is pretty hard. Some of it is trial and error. Hope that helps. Any other questions? I'm a bit, yeah, sorry.
My application is still on JDK 8.
Yes, okay.
Your recommendation, shall we go on 17 or 21?
So I would always recommend the latest, of course. So the question is, my application is still on 8, what should I do? And upgrade is, of course, I assume you're planning to upgrade. And should I upgrade to 17 or 21 directly? And that depends, I would say, on what your requirements or what can you upgrade to. Sometimes it's easier to just go to 17 because you might have libraries that only support that or something like that. But generally, if you can go to 21, do that directly. But you can do it in steps. I mean, start by making sure you run on JDK 11. Then what more do I need to do to go to 17 and next 21? Because once you moved past JDK 8 to 11, the problems usually become smaller. So, yes, a question here.
Is the garbage collection team involved in designing new features, or is that they invent cool stuff and you have to fix it?
Yeah. So the question is, are we involved when designing new, large, cool features like the ones that maybe Brian have talked about? And of course, yeah, the GC team is heavily involved in a lot of the big features in the Java platform, because how things are done will affect us and how well we can do garbage collection. So we try to make sure that the new features are implemented in a way that they will continue to support garbage collection in a good way. More question over there?
What happened to Shenandoah?
So, yeah, the question is, what happened to Shenandoah? Shenandoah is still alive and well. It's just that at Oracle, we're not the maintainers of Shenandoah. So Shenandoah was initially developed by Red Hat and is now the generational version of Shenandoah is developed by Amazon. And I'm not going to say when, but they are also working on a generational mode of Shenandoah. So hopefully that will come out soon. But since we're not the maintainers of it, I don't feel comfortable including it in a presentation like this. So it's still around. Hope that helps. Any more questions? I don't see anyone. So, well, again, thanks for listening. Hope you learned something today. Hi. Thanks.
I have a question.
All systems are nominal. Initialize Genesis sequence.